In this set of lecture notes, we're going to talk about one-dimensional motion. So later down the line, we're going to take the ideas that we learn here and we're going to generalize them to two-dimensional motion or three-dimensional motion. So for the time being, we'll stick to 1D, and before we even start actual conversation about motion, there are a couple of other quantities that we need to define, or rather a couple words that we need to define that we're going to be using throughout the semester. So let's start with the definition of a scalar and a vector. So scalar is a quantity that has magnitude only. As opposed to a vector, which is a quantity that has magnitude and direction. I'm sure you have seen examples of both of these quantities in everyday life. You probably didn't realize which one is which, or maybe you didn't even know that this this vocabulary words even exist. Now first, we need to define what it actually means, right? I mean, I'm giving you a definition of scalar and vector, but what exactly does this represent? So the word magnitude in general means how big something is, right? So we're talking about a value. Let me write that too. Okay, so there are different ways of defining it. Now, the interesting thing is that in the definition of a scalar and the definition of a vector, the word magnitude actually has slightly different meaning. So if we're talking about magnitude as defined for a scalar, that literally just means a value. So I can say length is 5 inches or temperature is -3 degrees, something like that. So that's for a scalar. This value can be either positive, negative, or 0. When we're talking about vectors, the word magnitude also tells us how big something is, but in this case, it's always positive. So this does not mean that vectors cannot be negative. It just means that magnitude is always positive, and then if something negative comes up, then it's going to be addressed by the means of direction. We'll get back to that in just a second. Some examples, something from everyday life. So for a scalar, mass, that's something that you already know. Notice how I didn't say weight, I said mass. Different ideas. We'll have to talk about that too at some point. Length, right? That's also something that you know. Time, number of people in the room, and so on. So there are all kinds of different measurements that you can make where there is no direction. It means it doesn't even make any sense to talk about direction if you're talking about number of people, for example. Now, a vector is something that has a direction. So again, something that you know from everyday life. Maybe you have heard of the term velocity. If you haven't, that's okay. We'll talk about that in just a minute. Maybe you have heard the term force. So that's a vector. Maybe you have heard the term momentum. And so on. So if you have not heard the words force and momentum, no biggie. We are going to talk about forces and momentum in this class quite a bit, actually, just not today. Okay? So this is what we need to know in order to be able to fully discuss what we're going to discuss for 1D motion. Let me also show you vector notation. So I'm just going to use capital V for any generic vector. So typically a vector is denoted by an arrow like this on top of it. Now this arrow just represents that this quantity is a vector. This arrow by itself does not represent this vector pointing to the right or anything else like that. So that just says that this quantity is a vector. A lot of times people get lazy or in a rush, and instead of doing a full arrow, you'll do something like this, like a half arrow. You might even see just a bar over it. I don't recommend using the bar because the bar is one of the notations for average. So that might come in handy for that. But if you're always consistent and always use that bar, I suppose that's not that big of a deal, and then you can do that. If you look at some articles or some textbooks, especially older ones, you may see a little squiggly line underneath a quantity. So that's not quite as often, not quite as commonly used, but it does happen sometimes. So just be on the lookout for that. And then finally, in printed text, the most common way to denote a vector is to make it bold-faced. Obviously, if you're taking notes, you're not going to make that bold-faced. So I think that this notation is probably the easiest one to see and the easiest one to use. But like I said, just be on the lookout for all of this other notations, especially if you're searching for some additional information on something somewhere. This, by the way, whatever quantity without the vector arrow, this would be a scalar. But if this scalar is used to represent magnitude of a vector, you also might see it written like this with absolute values. So absolute values represents magnitude. So if you ever see this written, or if it's implied, then this is the magnitude of vector v. And then of course, in this case, since we're using absolute values, that implies that the magnitude of a vector is always positive. You also might see it written like this with kind of double absolute values in calculus. That happens sometimes. So we're not going to be using calculus in this class, but there is no harm in knowing this notation, that it is often used in calculus. The last thing that I'm going to say about vectors for the time being, until we fully get into that, is the direction stuff. So there are two ways of addressing direction of a vector. The easiest way, that's what we're doing right now, is just envisioning a coordinate plane, right? So we've got an x-axis and a y-axis. All of you know this. So when something points to the right or up, it's going to be positive. When something points to the left or down, it's going to be negative. So for example, if I say that the velocity of a car is negative 5 meters per second, that would mean that it's traveling to the left or maybe south. So you can also call these axes north, south, east, and west if you want. Not always advisable, but it's okay. You can do that. So that's kind of what we're going to stick to right now while we're discussing one-dimensional motion. So for the most part, we'll talk about motion along the x-axis, so horizontally, but there is going to be a couple of instances where we're going to mention vertical motion. When we get to talk about 2 dimensions and 3 dimensions, we're going to use angle to represent the direction of a vector. So maybe a good idea to review your trigonometry a little bit. And we're also going to do that too in that set of lecture notes where we discuss vectors. So for now, just positive, negative, up, down, left, right. That's the only thing that we're doing right now. So now that we have these definitions under our belt, we can start talking about different quantities that actually describe one-dimensional motion. So for the most part, like I said, I will talk about motion in along the x-axis, but this could be any single axis doesn't really matter. What do we need to describe motion? Well, let's start with time. All of you know what that is, right? We use little t to represent time. I'm sure you guys know that too. The units are going to be seconds. I don't think I need to really define time, right? Everybody knows what that is and how to use it. The next quantity that we need is called position. So I'm going to use x for now, right? Because we're talking about motion in the x direction. But in general, there is a whole lot of different notations that vary depending on what source you're using. We can use y or z or r, s. R and s are used a lot in calculus as well. D, I don't recommend using d because it also relates to distance and stuff like that. So try to avoid using d for position. There are other notations as well. Like I said, for the time being, I'm going to just stick with generic x. Units of position are meters. I'm sure you guys know that. Remember, we're only using SI or metric units in this class. And the definition of position is location in space. Now, in general, space means 3D, right? Three-dimensional space. But for the time being, because we're limiting ourselves to one dimension, that basically just means location along the x-axis for now. Okay, so that's not the along the x-axis, that's not a generic term, that's just for the time being. We also need to define displacement. So notation for displacement is delta x. Some of you probably know this symbol. It's a Greek letter delta. And delta represents change. So in general, change is written as the final value minus the initial value. And this is for like any quantity, scalar or vector, any quantity that's changing, right? Final value minus initial value. So if I write delta x for displacement, I can also say that this is x final minus x initial. I'm not gonna really box this. It's not like an actual equation per se, but it is a definition, right? So this is how we find what displacement is. We'll find the difference between a final position and an initial position. So we're gonna call this change in position. And by the way, that subscript I and f, that's a very typical, probably the most typical way to address initial value and final value. So remember, position is measured in meters, so that means that displacement is also going to be measured in meters. Now, I should tell you this before we get too far into this. Technically speaking, both position and displacement are vectors. So I'm going to draw this vector arrow with a different color because as a rule, when we talk about one-dimensional motion, we don't indicate that x is a vector. It's kind of implied because motion could be to the right or to the left. Position could be to the right of the origin or to the left of the origin, but we just kind of ignore that piece. Now, when we get to 2D motion, it's going to be absolutely necessary to distinguish between vectors and scalars, but at least we don't have to worry about that just yet. So keep that in mind, right, that these quantities in general should be defined as vectors, and a couple other ones too that I'll define in a minute, but we don't have to worry about that too much yet. Okay. Now, let's just do a super quick example. So here is my coordinate axis with a 0. And then let me define x initial as 2 meters, and x final is -3 meters. See how I'm not writing x initial and x final as vectors? But the fact that that value could be positive or negative, that already tells you that position is a vector. So to the right of the origin, to the left of the origin. So displacement is from initial to final. Displacement is typically, vector is typically represented with an arrow like that. We'll also get back to that in a little while. So this kind of just shows that process of changing from initial to final point. And I could write this, right? Delta x equals x final minus x initial equals -3 meters minus +2 meters. I'll even put parentheses on it for clarity. So displacement is -5 meters. So interpretation would be the object, or whatever that is moving 5 meters to the left. So that should be pretty self-explanatory. The reason I'm showing you this is actually not so much for displacement, but so that we can talk about distance, as in distance traveled. I'm going to use that d for distance traveled. That's also a very typical way of referring to it, so I don't think I need to even show you any other notation for that. And to define distance, let's again refer to the same example here. So distance is basically how far the object has moved, right? So ask yourself right now, we said the displacement was -5 meters. How far did the object move? 5 meters, right? So distance is going to be always positive. Technically, distance is a scalar, right? So it's only got magnitude and it's always positive, so it's actually kind of boring. But we also need to be able to define it mathematically or algebraically. Well, okay, if it's just magnitude and it's always positive, you should be able to just write this, right? Distance is the absolute value of displacement. Yeah, I mean, that seems kind of self-explanatory, right? So we said displacement was -5 meters in this example, so distance would be absolute value of that, which is just +5 meters. Okay, that's nice. Easy, no problem with that. The problem arises when you have more complicated motion. So let's say you have something like this. So here is my coordinate system. Let's say that's my 0. X initial is -4 meters. There is going to be some kind of x intermediate, x1, whatever, 3 meters. And then let's say x final is -1 meter. So the way that this object moves, and I'm going to draw this a little offset for clarity, is it starts over here at x initial, travels to x1, then turns around and goes back to x final. If we find the displacement of this object, we're only doing final minus initial. So displacement actually doesn't tell us anything about how or by which route the object moved from initial to final. So if I found displacement of this object, I'm going to write this as 3 meters. But is distance traveled just the absolute value of that? Of course not. That's why I drew that little picture there, right? To see how the object moved. So it's not as simple to define distance as absolute value of displacement. You also have to take into account where the object turned. So if you want to still write it as absolute values, you can write it as something like this, delta x1 plus delta x2. So delta x1 would be displacement from x initial to x1. So that would be 7 meters. And I guess I can still keep the absolute value there, right? So from -4 to 3 meters. Plus And then what's the next piece there? So from 3 meters to -1 meter, displacement is -4 meters. We are taking absolute value of each piece individually. And then we get 7 meters plus 4 meters equals 11 meters. Okay. So if you want to define distance as absolute value of displacement, you have to pay attention to what's called turning points. So this here is turning point. That's where the object stops, turns around, and goes back the other direction. We use that term turning point quite a bit in this class in all kinds of descriptions of motion. So this absolute value of displacement, this is split, right, into however many pieces, however many intervals. I'll just make a little note here. Split at turning point. Right, so if there were 7 turning points, there would be 8 different intervals to consider. By the way, the word interval is also a good word. So it represents both interval in time as well as like mathematical interval. So think back to what you know about functions from math. Last thing that I need to tell you about distance is that it's also going to be measured in meters, right? Because we are still talking about some kind of something that's related to position or displacement. Next term is velocity. So velocity is represented by little v. I usually write it like this with a curly v to not get it confused with capital V. So unfortunately, we only have 26 Latin or English letters to represent all of the physical quantities that we have. So we end up reusing letters quite a bit. We also have Greek alphabet to use, and we do use a lot of it, if not all. We'll go through some of those symbols as well, like delta was one, right? So you just have to be very careful with notation. Proper notation in this class is not optional, it's mandatory, because by writing whatever you're writing, you're communicating your thought process to me and maybe to your classmates and to yourself, first and foremost. So anyway, I'm going to use little v for velocity. Now I have to be careful again, right? So velocity is a vector, so it's got magnitude and direction. Let me write that down. Magnitude and direction. Does anybody know what magnitude of velocity is called? I bet you know. Magnitude of velocity is called speed. So speed is a scalar, and it's magnitude of velocity. And then velocity is a vector, it's got direction. I should also probably tell you that speed is always positive as well. So like you're not going to say car moves at negative 60 miles per hour, for example, right? So speed is positive. Velocity is defined as rate of change of position. And since I'm being really careful here with my notation, I'm going to put vector notation on position, and I'm actually going to box it. This is both a definition and an equation that we can use. So rate of change of position. Rate of change of position with respect to time. Now this abbreviation WRT with respect to. So a lot of times when we talk about rates, we're kind of automatically assuming that that rate is with respect to time. And for a great majority of situations in this class, that's going to be correct. But still, if you want to be very specific and very careful in defining all of this, it's better to say it's rate of change of position with respect to time. You can also say the rate of displacement with respect to time, right? Because delta x is displacement. So however you want to write that. Units. What are the units of displacement? Meters. What are the units of time? Seconds. So the unit for velocity, and for speed, by the way, as well, is meters per second. Okay, meters per second. Now, we did talk about fundamental units and derived units. So this is our first example of a derived unit. So it's based on fundamental units. So you take unit for displacement, divide by units in time. That's the result. Let's keep going. The next term is acceleration. We use capital A for acceleration, and it's defined as the rate of change of velocity. Again, I'm gonna be careful with notation here and put vector arrows on this. Again, both definition and an equation for certain cases. So, rate of change of velocity with respect to time. Now I'm going to underline the word velocity because here it's very specific. It's velocity that could be changing, not just speed. So remember, velocity is speed and direction, right? So when we talk about rate of change of velocity, we can say that speed can change, or direction can change, or both. This little symbol here represents the basically just copying the previous line to the current line. So acceleration is rate of change of velocity with respect to time. And yes, it is a vector. So we don't really need to worry too much about this right now, but I might as well tell you. So we can kind of schematically compare velocity and acceleration, not numerically, right? Because they're different things, so I can't really numerically compare them. Oh, before I do that, I should probably tell you what the units are. So velocity is measured in meters per second. Time is in seconds. So the way that this is written is meters per second, or more commonly, this is abbreviated as meters per second squared. That's the notation for it. Meters per second squared. So it literally means by how many meters per second does velocity change every second. So as far as relative directions are concerned, of velocity and acceleration, I'm going to schematically represent these as arrows, which is a vector notation anyway, which we'll discuss later. So let's just say that I have initial velocity like this, pointing to the right. And there is also acceleration pointing to the right. So for example, let's say we have a car that's already driving to the right, and then the driver steps on the gas, and then the car also accelerates to the right. So the result of that, velocity and acceleration vector both pointing to the right, is larger velocity or larger speed. Now, I haven't mentioned this yet, but if we're talking about vectors, then the length of that arrow represents the magnitude. So here, the length of the velocity arrow represents the speed. So velocity and acceleration both point to the right. That results in speeding up, right? As in, the object starts moving faster. Well, let's also go through the signs. To the right, we said was positive. This one's also to the right, and the result is also to the right. So everything's positive here. So we know that the object is accelerating. Let's do one more. I'll start with the same velocity here, but this time acceleration is going to be in the opposite direction. Does anybody know what that is called? Yeah, in English you can call that deceleration. And the result of that is slowing down, right? Smaller final speed. Let's go through the signs. To the right is positive, to the left is negative, and this is still positive here, smaller, but it's still positive. So this is where it gets a little bit tricky. In English, and perhaps some other languages, we use several words to describe acceleration. So we just said acceleration by itself means that the object is speeding up. Deceleration means the object is slowing down. And there's those other extra words that are speeding up, slowing down, right? In physics, we don't need any of that. We just literally use one word for that, acceleration. And that's it. So acceleration means velocity is changing. And by the way, negative acceleration doesn't always result in deceleration. So it's confusing in that respect to use those English words because it kind of doesn't get you anywhere. So let me show you an example of that. Let's say I have this as my initial velocity. And I'm going to have this acceleration as well. So this time both of these quantities are negative. But what's the result? If the car is moving to the left and the driver steps on the gas, isn't the car still going to speed up? So in this case, this negative acceleration is actually not deceleration, right? So it's still acceleration. That's why physics language is a lot more precise and a lot less confusing. So we're just saying negative acceleration. That's it. And what about this case? If I have V initial like this, and I have acceleration in the opposite direction, what's going to happen? The object is going to slow down. And yet, if you look at the signs, velocity is negative, acceleration is positive, final velocity is still negative there. So again, English is not always the best thing to refer to. Physics language is better. It's more precise on one hand, and on the other hand, it's less confusing. So acceleration just means change in velocity. Notice the relationship here is that speeding up happens when velocity vector and acceleration vector are pointing in the same direction. So it's obviously very important to understand what that direction is, and for that we definitely need vector description. When an object is slowing down, that happens when velocity vector and acceleration vector are pointing in the opposite direction. Okay. Finally, I will show you one other case. We don't need to worry about it right now because we're only doing 1D, but later down the line we will deal with the case where acceleration vector is perpendicular to the velocity vector. So in this case, direction changes, but speed does not. So in English, we would probably use the word turning or something equivalent to that. In physics, we still call that acceleration. So this happens when velocity vector is perpendicular to acceleration vector. And notice that none of this description would be possible without knowing what the vector is, without being able to represent descriptions, right? Directions. Okay. Couple more things here. So we're talking about, well, we talked about displacement. We talked about velocity being displacement over time. We talked about acceleration being change in velocity over time. Can acceleration also be changing? Yes. So I'm going to show this to you. We're actually not going to use it in this class, but you still need to know that such a quantity exists. So the next term would be called J. And J would be change in acceleration over time. J stands for jerk. So I'm, again, boxing this. Okay. But in this class, we're not going to really deal with that. I will show you units really quickly. This is meters per second cubed. Okay. And by the way, jerk can also change. And this process of changing all of these quantities can repeat forever. So everybody always gets a good chuckle out of it when I tell you what the next iterations of this change process are called. The next one is called snap. So change in jerk is called a snap. The next one is called a crackle. And the next one is called a pop. And no, I'm not pulling your leg on this one. So all of this changes. So change in jerk is called a snap. Change in snap is called a crackle. Change in crackle is called a pop. Those are legit quantities. They have legit values. So basically, you just keep dividing these units by seconds, right? Because each of these iterations, each of these changes happens over time. So they're legit things. But do we really need them? Not really. The only time when these quantities matter is when you have a lot of changes, right? And not just change in position or velocity, but a lot of these changes are happening, and especially if they're happening quickly. So maybe something like accelerating a race car or launching a rocket into space, something like that. Maybe that kind of engineering application would require some of these quantities. Jerk, for sure. Snap, crackle, and pop? Maybe you would be calculating something like that if you were an engineer launching a rocket into space. But maybe it's really not even that essential even there. So in this class, we definitely don't need to worry about it. So in this class, we kind of draw a line right here, okay? And what we say is that most of the time, we're going to stick with constant acceleration. Most of the time, acceleration is constant. So you should know the meaning of that term constant. Constant means not changing, specifically not changing over time. Okay, so we're going to have to address that, and we're going to have to use that quite a bit. Now, it's possible for position to be constant. It's possible for velocity to be constant. But specifically for acceleration, if acceleration is constant, we have a very special name for that. We call that kinematics. And we're going to have a separate topic on one-dimensional kinematics that's coming up. So out of the stuff that we did in this lecture, well, you need everything. So obviously we started with definitions of vectors and scalars. So that's going to kind of propagate through the entire semester. Talked about directions very briefly. That's also very necessary. And then we're using time, position, displacement, distance, velocity, and acceleration to describe one-dimensional motion. And in principle, you would need all of those quantities to completely describe one-dimensional motion. So relative directions of velocity and acceleration, important because you can use them to explain kind of how motion changes. We'll come back to that too. And then I showed you this briefly, but all of those things past acceleration are not really that essential.